It's a pleasure to be here. I'm one of the OG EGD crew from way back when, 6 years ago. So today I wanted to share with you some of my thoughts about how we can do EGD-related research and some of the, I think, lessons learned from our lab that may be relevant to you. As Nate said, I'm at MIT. I'm an associate professor in mechanical engineering, and my research group, the Global Engineering and Research Lab, focuses on the creation of technologies for developing and emerging markets. One of them is this brackish water desalination system. In this picture you're going to hear about a little more. But the main theme I want to really come through today is I think a lot of our success has come through aligning value propositions where we can do science, we can chase after a meritorious economic and business opportunity, and also chase after some real-world impact. So to start out, I think it's worth reflecting for a second about why is engineering for global development challenging? Well, we can look at metrics of human health and well-being like the Sustainable Development Goals. And just from a get-go, you know, these are advancements on the Millennium Development Goals, half of which were met, but the other half weren't really met by the year 2015. And even meeting those goals meant just having the population that faces these challenges. But, you know, as a baseline, there's still, you know, 1 billion people in extreme poverty, 2 billion people without clean water, et cetera. But I think what's interesting about looking at these goals through an engineering lens is that you can see that many of them could benefit from our intervention, things like clean water, like energy, right? And what's particularly interesting to me is that many of these challenges are either solved or greatly diminished in countries like Canada or the US. Like, I don't think any of us worried about the water quality if we drank water this morning, and nobody worried about if our toilet would work, right? And so what's interesting to me is that we've solved a lot of these problems, or at least greatly diminished them, in countries like this, but they haven't mapped over to poor countries. And I think the reason is because of a price-performance mismatch. So if you take any family of technology, you know, let's say take cars for an example. You may have like a Ferrari type solution which costs a huge amount of money and gives a relatively high amount of performance, and like your Toyota Corolla type solution which gives you your baseline performance but costs a lot less. And so any technology is going to lie on that curve as you add and remove features. And so what I think is happening in poor countries is that people are still demanding a baseline level of functionality and performance. Like, nobody wants a semi-functional toilet or like semi-clean water. But the problem is they may not be able to afford what we pay for that same solution here. You know, we may pay up here, but they may be able to only afford there. And so this creates, I think, a challenging situation, but also a great opportunity for us as engineers, in that there's no way to adapt our way down this existing technology curve to come up with a solution. We have to somehow create a disruptive solution. So what my group does is looks at this through 3 phases, where first we do a lot of socioeconomic and technical detective work to try to understand where is this new price performance point that we need to hit to satisfy the market needs, and to juxtapose that with where does existing technology lie and how far off are we. Then as an academic group, I think we're in a wonderful position to leverage research, leverage engineering science, leverage our insights into the physics as well as the market needs to make this disruptive leap to create that high performance, low cost technology. And then we're always looking globally, if we can as well, not just thinking about what's that one solution we can make for a poor country, but how could we grow that to an entire family of technologies that can engage rich and poor countries concurrently through this process that's been termed recently the buzzword reverse innovation, right? So this is how my group looks at the problem. And I got started in this line of work, God, more than 10 years ago now, with this product called the Leverage Freedom Chair, which is an off-road, all-terrain wheelchair designed for rural areas of developing countries, like you see in this picture. And the trick behind the design is that to go fast, you grab down near the pivots of the levers so you can push through a big angle every stroke. And as the going gets tougher, if you need more torque at the wheels to, say, go uphill or go through sand or mud, you can slide your hands up the levers to produce that greater torque. So with this very simple technology, our chair is about 80% faster than a regular wheelchair on the road. It's about 40% more efficient to propel, and then when the going gets tougher, you just slide your hands up the levers and you can produce about 50% more torque at the wheel than you could with a conventional push rim. So back when I was in grad school, many years ago, we were working on this. We were trying to make this high-performance, low-cost, all-terrain technology, and we started to get some press around this project. And people in the US and Canada started saying to us, why would you only make a high-performance, low-cost, go anywhere, easy to repair, super robust, yada, 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 technology for the developing world? We want that too. That would benefit us as well. And this clued us into the idea that we could take this same product platform and add and remove some features and make it a multi-market global product. And so that led to this product, the Grit Freedom Chair, which will hopefully start. I don't know why this video is not starting, but let me go back. There we go. This product, the Grit Freedom Chair, where you can see this shares the same DNA as our Leverage Freedom Chair, developing world variant, but it's an all-terrain, enabling, go-anywhere type mobility aid that's not a medical product. This is really an enabling, life-enhancing type device. So with this same platform of technology, we were able to start a company, Global Research Innovation Technology, and create two product lines based on that same DNA. So we have the developing world product made in India, and then the US variant, now made in Taiwan, but assembled in the US and distributed all over the place. And I want to be very clear that this is not a buy one, give one type strategy. These are two different business strategies, one trying to leverage high volumes at relatively lower margins in developing countries, and one trying to leverage higher margins but relatively lower volumes in wealthier markets. So going through this experience with the Leverage Freedom Chair and starting Grit really made me experience this firsthand, this process through which we can engineer global development. So, we created the LFC, this high-performance, low-cost developing world product, and then also successfully adapted it back to wealthier markets where it shared the same DNA, but met those specific market needs. So in my talk today, I'm going to tell you about two current research projects we're doing on brackish water desalination and drip irrigation that I think align really well with this three-stage process of how we're trying to engage emerging markets and create new technologies. But before I get into that, I think it's worth taking a moment to reflect on what elements I think are required to do successful engineering for global development research. So the first thing I'm always trying to ask myself is that, are we going after a meritorious problem? And what I mean by that is, are we actually going after a compelling development challenge? Are we just making some little widget for a single village in one part of the world, or are we actually going after something that could impact a large amount of people in a compelling way? I also ask myself, is there an unmet economic opportunity? Is there a way that we could take a solution and scale it through free market mechanisms because users recognize the value in it and want to invest in it? And I think about, do we understand the metrics of performance that must be satisfied in order to create a successful solution? Or are we just qualitatively looking at the problem? Because I think when engineers know what the actual problem is, we're really good at solving it. And then what I try to dovetail with this is the technical merit behind the projects we look at. So I ask myself, are we actually looking at an engineer for global development problem, or is it a marketing for global development, or giving away money for global development, right? Or does it need engineering to solve? I ask myself, can I leverage technical insights to create a solution? Can I leverage an understanding of the physics and the thermodynamics behind the problem to actually see how could we create a solution? And then if we're creating research, I'm always asking myself, must new knowledge be created in order to solve this problem? And knowledge that we can publish and fit within the conventional academic metrics. I see a lot of EGD projects fall short because they don't center in this Venn diagram. I think we all see like undergraduate service learning classes where they don't have time to understand the problem and they don't have the time or maybe technical skills to actually create a rigorous technical solution. You may be familiar with like Jugaad solutions, like hacked together solutions that may kind of work, but they're not rigorously engineered, optimized solutions. And then looking the other way, I see very commonly very well-intentioned faculty members that want to use their research expertise to solve global problems, but they have no context around them. And so there'll sometimes be a tenuous connection between their research and a development challenge, but often when they start the research, it's just business as usual. They're just doing their regular research. So I think that center point in that Venn diagram is really important. And then the final point of this Venn diagram is I think you have to align your value merits behind whatever project you're working on. And what I mean by that is you have to think about who will fund your work and what do they care about. And it may actually be different than what you care about, but maybe you can find that nice shared space where you can both work and mutually benefit. I think about who's positioned to disseminate the work. Probably not me, I'm an academic. So who could actually take our good solution to market? And I think about who's going to make money off this, who's incentivized to work on this and disseminate it. And finally, I think about what is my own value proposition? Do I want to impact lives? Do I want to make money? Do I want to educate students? Do I want to publish research? Could we do all of the above? So we take a lot of time to try to figure out this Venn diagram. And I think, once we answer all these questions and we're pretty confident, what we focus on is the technological keystone at the center of this. And what I mean by that is there's often a research problem that we can really sink our teeth into. It's a small subset of the overall problem, but if we create that technological keystone, our partners are well positioned to build the arch of the rest of the solution around it. So I'm going to give you some examples of hopefully how we're actually doing this. And the first is about brackish water desalination. So this project goes back about 6 years when we started interacting with a large irrigation company in India called Jain Irrigation. And they said to us, most of our clients are poor farmers. They live in rural areas. Many of them don't have access to clean water. We're an irrigation company. We work with water. We should be able to do something about this. But what do? And this was a critical point in the project because I think the classic academic response is after that conversation we say, we'll go make you a water filter, or we'll go make you an RO system or something. We'll go solve the problem. But we didn't actually know what the problem is. And so it was so important to take a massive step back and understand what does dirty water look like in their target market, which was India, and what insights could we maybe leverage to create a solution. So the first thing we tried to understand was kind of the socioeconomic space behind the problem. And it turns out that the most prevalent contaminant in India is salt. 60% of the land area of the country has salty enough water, and it's shown by any color other than blue in this map, salty enough water that you can taste, and that's above the safe drinking threshold set by the World Health Organization. This disproportionately affects people in rural areas. 70% of the population of India gets their drinking water from groundwater. And in rural areas, most rural villages will not have reliable grid access, which makes it difficult to take the salt out of the water. And our target market here, we found, was villages of 2,000 to 5,000 people, which accounts for a quarter of the country's population. It's the median village size. So that kind of gave us the lay of the land of the problem affecting people. And then we also had to get a sense of what are the economics behind this? And a couple years into the project, we teamed up with Tata Projects, which is an infrastructure company. And they have a successful business making village-scale reverse osmosis desalination systems. They've done over 2,000 of them throughout the country. And what they clued us into was that if they're on-grid, their systems are economically viable. The village can pay for the capital and recurring costs off the sale of water. Once they go off-grid, the budget's blown. The capital cost more than doubles. And so we learned that off-grid could be a great opportunity, and that made us start thinking about solar irradiance maps, which is what's shown in right here, and how they overlap pretty nicely with the saltiest areas. So where you have the saltiest water, you also have the greatest solar irradiance and the greatest energy potential to take the water out. And then the final part of this detective case was thinking about what technologies could work for us. And so we looked at any technology we could find that could take the salt out of the water. And the two leading candidates were reverse osmosis, which I'm sure you're all familiar with. That's kind of the leading way to do it. And a technology called electrodialysis, which has been around since the 1950s. It's used mostly in larger industrial applications, not used in village scale. And so what we realized by diving into the physics and thermodynamics of this problem was that reverse osmosis requires twice the energy compared to electrodialysis per unit volume of water created for the salinity ranges you find in India. Now, why that was so important as an insight was that when we want to go off-grid, the capital cost of our power system can get cut in half. And then the other big merit is that for these size RO systems currently used in villages, they waste about 60% of the water that come into them, whereas electrodialysis can cut that wastage down to less than 10%. And so the moral of the story here is we took actually 2 years to put together this socioeconomic and technical detective case, and that is what gave us, I would say, the disruptive insight that photovoltaic-powered electrodialysis could make a big impact in India. And now, since then, we've led competitors by about 2 years by realizing this. And also because we laid out this problem in a solution path, we were able to attract a lot of sponsors that are keen on helping us make this a reality. So what's happened since then is, we did all this analysis, but then we wanted to, put rubber to the road and see, does this actually work? So serendipitously, about a year after we finished this analysis, USAID came out with a program called the DSAL Prize. It was a multinational prize program to make off-grid, renewable-powered desalination systems about the same size scale as what you'd want for an Indian village. So we competed in that, we made our first scale system, and we ended up winning that prize. That got us a good foot in the door with USAID, which then led to other field pilots that they funded, first in Jalgaon, India, and then in this past year, we completed a pilot in Cheluru, India, as well as one in Gaza. And so the moral of the story here is that we couldn't just do analysis with this technology. We had to test it in the field to understand the pain points, and I think really understand how could we leverage research to make electrodialysis a viable solution. So one of the things we ended up doing was look at how could we actually optimize a photovoltaic electrodialysis system for a village context by really understanding what are all the parametric relationships behind how it works. How does water and energy flow, and how do the main capital cost drivers of the system like water tanks and membranes and solar panels and batteries all interchange and interlock in order to set your capital cost? And could we look at that full system integration and figure out how to take money out of the capital cost of the system? Well, what came out of that parametric study was realizing that we can cut the capital cost by about 40% compared to how these systems would typically be designed in kind of a serial process where you say how much water you need, how big an electrodialysis system you need, and then how big a solar system you need. Instead, you can co-optimize them at the same time, and we realized we could leverage tricks like on sunny days, we could produce more water that we could then use on cloudy days. It's cheaper to store energy in water tanks than it is in batteries. If we make the system flexible in its operation, so seasonally or even day by day it can change its production, we don't have to do a set production amount every single day, even if it's cloudy. So, we modeled all of this, but then it was important that we made this. And if you go to Wei He's presentation a little later in the conference, you'll hear about how this thing actually performed and how we were actually able to validate that optimization model. We also understood the pain points about the main capital cost driver of the electrodialysis stack. This is a stack of ion exchange membranes with electrodes on each end, which is the main capital cost component in the system. So because we took the time to dive in the physics, understand how it all works, we were able to first optimize a current architecture for as low as cost possible, about $5,000. Then we were able to say, boy, well, if we change the geometry of this thing, we can cut that cost down to about $1,700. And then always facing this pressure of how do we get that high performance at low cost really catalyzed an insight into realizing we could operate the system totally differently. Instead of at a fixed voltage, do it at a variable voltage. And this insight enabled us to either double our production rate or half our capital cost. And that has led us to a system that we think would be under $1,000. So again, the moral of the story is we wouldn't have realized how to make this so much cheaper if we didn't dive into the physics and really leverage our engineering muscles to figure what's going on. So what we're looking at now is, again, not just saying, can we just solve the problem of village areas of developing countries and how to purify water? That's certainly one of our main focuses. We're also thinking about how can we leverage this engineering understanding to, say, go after home use systems. Home use RO systems waste about 80% of the water that go into them. And so we've been working with the market leader actually in India to make electrodialysis-based home use systems. We're also thinking about disaster response. We can now say, what if we take the battery out of the system so we can put it on an airplane? Because there's limits on how much energy you can hold in batteries on an airplane. And imagine you can make this batteryless system, you throw it on an airplane, and you can get it to, say, like Puerto Rico, right after the hurricanes last year, and bam, immediately set up a clean water system within a matter of hours. So we're starting to work on that. We're also thinking about, could we do like humanitarian response for refugee camps or like forward operating bases for the military? And also thinking about, what about municipal systems? In India right now, when you build an apartment complex, it's really common to put an RO system on top of the building, which provides all the water to the apartments. So that high wastage is being magnified through all the water use, not just drinking water use. So maybe we could put electrodialysis systems on the top of those buildings. So again, the moral of the story is like, we're not trying to see one solution path, we're trying to leverage our insights to see many solution paths. The next example I want to talk to you about is irrigation. And so this has a similar backstory in that about 6 years ago, we were interacting again with this company, Jane Irrigation, and they started cluing us into the big untapped market and the big development impacts that could be enabled by expanding their business of irrigation and water-efficient irrigation systems, particularly for rural areas of developing countries. And from a development perspective, the big motivation behind that is that there's about 500 million, with a B, small-scale subsistence farms throughout the developing world. It accounts for about 2.5 billion people. And the highest development intervention you can do for these folks is enabling them to irrigate, because they can grow more and higher value crops, make more money, and get out of poverty. Now, the rub is that the conventional way to allow them to irrigate is with flood irrigation, like you see in this picture, where you dig channels and flood water in. Now, why that's a problem in a country like India is that already in the next 10 years, India is expected to have its consumption rate of clean water exceed its replenishment rate. You can't just take 100 million more farmers and have them suck water out of the ground. And already 70% of the fresh water used in the country is for agriculture. So the silver bullet here potentially is drip irrigation. So this is a means of irrigating crops by just dripping out the exact amount of water the crop needs, so you minimize water loss to evaporation and drainage. You can grow a lot more crops than rain-fed irrigation, and you can cut your water consumption by about 60% compared to regular flood irrigation. Now, from Jane's perspective, from a global market opportunity, this is a schematic showing the relative areas of total cultivated cropland in the world, in the green circle, how much of that cropland is irrigated through some means with the blue circle, and the pun intended drop in the bucket with a little red dot in the middle, which is how much cropland is drip irrigated. So Jane looks at this and it's like, wow, we can grow our business massively, make a lot of money while impacting a quite disadvantaged population. So we started thinking about this with Jane and started thinking about the physics behind how these systems work. And this is a very simple schematic of a drip irrigation system that's pulling from a surface source of water. This could be like a pond or a canal through a pump, and then you have the pipes that deliver the water through the drippers to the field. Now, the big challenge from a physics perspective right now with drip irrigation is that the drip emitters need about 1 bar, 1 atmosphere of pressure to achieve the correct flow rate that the crops need. Now, why that's such a challenge is that when you go off-grid with drip irrigation, it costs about $3,000 per acre to make either a solar or diesel-powered system, and 70% of that capital cost is in the pump in the power system. So again, by understanding the physics behind how this works, we realized that if we could cut the pressure at the dripper down to about 0.1 bar, we could cut the overall pressure in the system by about half, cut the pumping power in half, and cut the capital cost by about half. And if we can get it down to that point, given subsidies that are pretty common throughout India, we could get it down to a cost to the farmer of about $300 per acre, which would be affordable in about a 1.5 year payback period. So again, we're trying to benefit the lives of folks like this, but we're also thinking about this the whole time about, could we benefit the lives of folks like this? Like California is water constrained. You know, drip irrigation is used globally. Can we reduce the use of water and increase crop productivity globally with this technology? So to do this, we had to make what are called pressure compensating drip emitters. And what that means is that our drip emitters, once they feel a pressure and they come up to what's called the activation pressure, they'll start distributing a constant flow rate even if you increase the pressure applied to them. Now, why this is important is that the drippers near the pump feel a higher pressure than the drippers at the end of the line, but you want a uniform distribution of flow throughout the whole field. And again, the issue with existing technology is that activation pressure usually happens around 1 bar, but we again want to get it down to about 0.1 bar. So if you open one of these up, this is what's called an online drip emitter. This would be used for like tree crops. there's two pieces of injection molded plastic, and in between them is a silicone membrane. And that silicone membrane is flexible and interacts with a bunch of flow control features within the dripper. So all this geometry helps manage the water flow and create this pressure compensated effect. Now, an interesting aside is that when we started looking at this, we realized that the first patent filed on this type of flow restrictor was filed in the mid-1940s. This technology was popularized for irrigation in the 1970s, starting in Israel. And from all we can find in the literature, as well as all we know from our partner, Jane Irrigation, which is the second largest firm in the world, billion-dollar-a-year revenue business that works on this stuff, the behavior of these drippers was never mathematically characterized. And so what we tried to figure out was, well, what if we characterize the fluid flow and how it's controlled by the orifice, and as the water flows over this land, and then that silicone membrane presses against the land and restricts that water through the channel, could we characterize that fluid-solid behavior interaction and then optimize these drippers for a much lower activation pressure? So we did that, we characterized it, we put it into a genetic algorithm, we optimized it, and what came out of that was we were able to make variants of these drippers that have an activation pressure of 0.15 bar. And here are 3 commercial products all around 1 bar of pressure. I want to point out that this is actually our dripper. It's made exactly the same way, exactly in the same molds as the commercial products. All that's tweaked is the little geometry features inside the dripper, but it doesn't cost any more to make. And so what's been so exciting about these results is that if you are a farmer already using drip irrigation, you can just plug these drippers in and cut your energy costs by about a factor of 2. And so, like, depending on what crop you grow, that can almost double your profit margins. Farmers really like this, right? Because they obviously save money. And if you want to go off the grid, why this is exciting is it can cut the capital cost of your overall drip system by about 50%. So again, we did this in the lab, we made some prototypes, but it was important to test it in the real world. So over the last year, we've been doing a pretty large-scale field pilot in the Middle East, sponsored by USAID, at 9 field sites in Jordan and Morocco. And again, we've been testing our drippers at that low activation pressure of around 0.15 bar, and conventional drippers need about 0.5 to 1 bar. And here's kind of a snapshot of results from 3 places through this pilot in Morocco. And so what I want you to see here is that these are all showing our dripper in blue versus traditional drippers and the uniformity of water distribution through different days of the pilot. And we want to be at or above these dashed lines, which are the industry standards for how uniform the water's distributed. So what you see here is that we were good enough in most cases, and we were good enough at 43% less pumping energy than the existing products. So that was the objective. Do the job for half the energy, and it's working. Another thing we're doing right now is we're trying to fill out the whole portfolio of different dripper designs and particularly create what are called inline drip emitters. So these are emitters mounted right inside the lateral pipes, and they control the flow of water coming out. And so what we've been able to do is follow the same process and characterize parametrically the pressure flow rate relationships of these drippers. Here's 3 different flow rates in our theoretical models versus actual experimental theory. And we've been able to refine this model and get it accurately enough that we've now been able to optimize this to, again, with these drippers, hit a 0.1 bar activation pressure, whereas the conventional ones have a 0.5 bar activation pressure, so 5 times reduction in that pressure. And so Jaya, who's over here, is going to be giving a talk about this a little later with her new ultra-low pressure dripper design. So the moral of the story here, oh, sorry, one more thing before I get to the moral of the story, is that what's been cool about this project is, we're making these low pressure drippers, and then the Inter-American Development Bank reached out to us and said, you know what? In high altitude regions of the Andes, it's quite common for the government to build dams for farmers where they can catch water, they can send it down to their fields through a pipe, they have valve boxes, they open those valves and they can flood their fields. What if you could run your low pressure drippers under gravity fed water instead of pumped water? Because even with our low pressure systems, pumps are still about 60 to 70% of the capital cost of the system. We could potentially do it without pumps with this existing infrastructure. So over the last year, we've been doing a feasibility study with them, and it turns out, yeah, it's pretty common to have about 10 meters of elevation between the fields and the dam, which is enough pressure to run our drippers as well as run it through filters and through the pipes. So now the moral of the story is what we're trying to do is not just make low-pressure drippers, but create the whole suite of technologies and whole breadth of engineering theory that enables us to design these systems for many different situations, different geographic contexts, different crops. So we're working on online and inline drippers. And we're also looking at how do we optimize the system if we have solar power, grid power, gravitational power, and how do we store energy, maybe through a combination of gravity and batteries. So if we can solve this, then hopefully we can point to any spot on the Earth and say, here's how you'd make a drip system work in that context. So some final thoughts about what I think is really important in doing this work. The first is when you create a technology, you have to realize that it's going to go through this kind of iterative and development and evolution cycle where you'll first come up with an idea and you'll innovate it, you'll validate it, ideally then you'll commercialize it, and then hopefully then you'll disseminate it. And I think the first point that's super important to remember is this cycle starts and ends with end users. And I think all of us in this room are pretty attuned to that like we're trying to address user needs, right? And it's so critically important to engage these people, not as just folks you talk to, but really as partners and acknowledging that they have information that you don't have and they will have insights that you don't have. And then what I think is important is that as you start this innovation cycle, realizing where you lie. And me, as an academic at MIT, I have to recognize my limitations, that I'm only best positioned to come up with this innovation and maybe first prototyping and testing stages, but there's this chasm that exists going from the academic prototype to the commercial product. So in the case of brackish water desalination, like you see in this picture, it was so critical for us to form partnerships with stakeholders that could get us around this cycle. So it was important to work with folks like USAID and UNICEF that can do translational research, that can fund us to take our prototypes onto the field and see, do they work or why don't they work, and how should we invest more research to make them work. We're now interacting and working with Suez, the market leader in making electrodialysis systems. And then we have a long relationship and funding from Tata Projects, who sees the market opportunity and is really well positioned to do the system integration and dissemination, not only in India, but globally. Tata is part of the Tata empire, so it's a big multinational firm. So I encourage you to think about who are the stakeholders that represent each link in the chain going from the inception of an idea to implementation in the real world, identify who they are, and understand their needs and constraints and requirements and try to satisfy them in the design process. If you only design for these folks, you may miss the needs for all these other folks in order to get a solution out to market. I also want to touch on how important it is to align value propositions with funders. And I'm sorry about the video, but maybe it'll play this time. There we go. So it's so important to align your value proposition with different funders, and that's going to change a lot depending on who your funder is. So for example, I'm showing the snapshot of another research project we do on high-performance, low-cost prosthetic limbs. And a lot of the research that we've done is in the topology optimization of how to tune the stiffness and geometry of this foot, such when a person walks on it, it induces very close to able-bodied motion and loading. And so for a sponsor like NSF, they want intellectual merit. They want to understand the research value of articulating the physics and biomechanics of how you tune these prosthetic limbs, and they care about broader impact. You know, can we make this technology work for really underserved populations in the developing world? This foot will have a very low-cost manufacture that's about 3 orders of magnitude lower than other limbs on the market. But also we thought about, could this be valuable for other folks? And we're actually funded by the Department of Defense on this project. And actually, for a long time, I would go down to DC and talk to program managers and say, hey, we could make a low-cost foot for soldiers. And they'd say, we don't care about low cost. We're the military. We spend tons of money. What we care about is ruggedized products. And that made me realize that with this same theory, same research, same theory, we could optimize and design really ruggedized feet that you could take out to the field. You could get them wet. You don't have to recharge them. If you break them, well, they're relatively low cost than other feet, but we could make that military value proposition with the same fundamental research. And also, by talking to program managers, we realized another value proposition, that right now there's a congressional mandate to make improved feet, particularly for women, who have to too often use men's feet that are too big and too stiff. So with the same theory, we can say, hey, given your body weight and body size, we can make a foot exactly the right stiffness and size for you. As another example, a funder like USAID, they care about development impact. You know, for our desal work that they sponsor and our drip irrigation work, they want to see how you save water with your technology. And USAID cares about translational, not fundamental research like NSF. USAID does not have deep enough coffers to fund fundamental research. They need a good bet. They need to invest in something that has a high likelihood of working so they can go back to Congress and say, hey, this was a good investment of taxpayer money, right? So you have to think about that. You can't just pitch them a fundamental science project. You have to show how you're going to make an impact in the real world. And we've had a really nice symbiotic relationship with them, I think, in being able to say, look, we're going to do the field pilots. We learn from that as well, but we're also going to use some of your funding to do some of the more fundamental research. But it's a win-win. And they're like, yeah, we're good with that, as long as you're doing the translational work. And then finally, a funder like Tata Projects, a corporate sponsor, you know, you have to understand what they're going after. For them, they want to go after off-grid desalination because they can't access that market, and they need to make money. And they could care less about the research. They want the parametric design rules that tell them how to make systems for different contexts. And I want to touch on one more, I think, interesting element of the funding space right now is with the current presidential administration, where I was having to think about how do we benefit USA and Americans and this America First ethos. And this is not a comment on whether that's good or bad. It's a reality that we keep hearing from our program managers. And so even though I work on international development technology, I have to think about Suez makes all its membranes in Massachusetts. Jane has production in California. If we're successful, we will create American jobs. And we say that narrative in our proposals. And so it's not an either-or thing. It's we can say, look, we can benefit the US while also benefiting disadvantaged populations. So to wrap up, I encourage you to think about this pictorial view of how you could do engineering for global development. And I encourage you to take the time to really understand what problem you're trying to solve. If you really dig into the socioeconomics and technical factors and see that, you know what, you have to be here and there's no way to work your way down existing technology to get there, you will put yourself in a necessity is the mother of invention scenario, right? You have to invent to jump to that new point. And if you can articulate that, you're going to see the metrics of performance you'll have to satisfy to have a successful solution. And I think all of us here are in a wonderful position to leverage academic research to make this disruptive leap. That's what academia is here for, is to use those insights to create those revolutionary technologies. And certainly for us, it comes from this intersection between really trying to understand the market and the socioeconomics and really trying to understand the technical space. And then what I think is exciting about this too is that you can draw this whole plot before you design anything, right? And you can identify where this point is and start thinking to yourself, boy, if I could create this high value, high performance, low cost solution, would that have some value in wealthier markets? And could I think about creating a whole family that will engage rich and poor markets at the same time? And so what's exciting about the projects I told you about today is this is all happening for us in real time. So with our brackish water desalination, it started with Tata saying, hey, there's this big unmet market off-grid. And then UNICEF and USAID and Tata invested the money to make those disruptive leaps. And now actually we're funded by the US Bureau of Reclamation to make variants of our technology for the American Southwest, because there's actually good economic merit to make localized desal systems instead of pumping water over long distances to serve those communities. All the same technology, but pitching it to different value propositions of these different funders. Same goes with the irrigation project. Jane said, massive untapped market of poor farmers off the grid. Jane and USAID invested a lot of money to create this technology. And now what's happening is that USAID brought it to the Middle East. The Inter-American Development Bank is bringing it to Latin America. And Jane is a multinational company very well positioned to disseminate it globally. So with that, that concludes my talk. And if you want to see more about our work, you can check out gear.mit.edu or ping me at awinter@mit.edu. And I encourage you to check out our talks at the conference. You can take a snapshot of this, or if you search me on the app, you'll see the list of all these talks. And all but one is actually an EGD-focused talk. So thanks very much for having me, and I look forward to your questions after. think that was right on, 40, yeah.